Welcome to Statistics, Chapter 5, Lesson 5, the multiplication rules and tree diagrams. So the general multiplication rule is that for any random process that events A and B both occur, we can find the probability using the formula. The probability of A and B happening is the probability of A happening times the probability that B happens, given that A happens as well. Now, remember, probability of A happening is just the probability of A. Probability of B happening given A would be the probability of B and A divided by the probability of A, which would then just reduce there and get us probability of B and A, which is the same as A and B. So with independent events, we can just multiply the probabilities of A and B if probability of since the probability is going to be the same for both. We can also use tree diagrams, branching diagrams, to show the sample space of a random process that will use multiple stages. So if something happens and then a second thing happens and then a third thing happens and there are different probabilities all the way down, we can use some tree diagrams to figure that out. So the probability of each outcome needs to be shown on the corresponding branch of the tree. All probabilities after the first one are conditional, and then every outcome is shown on the corresponding branch. So, example 1. About 55% of high school students regularly participate in a school athletic team, and roughly 6% of these go on to play on some team in the National College Athletics Association. So we need to make a tree diagram of the information that we have. So first, we are talking about people who play a sport versus people who have no sport. The people who play the sport, again, 55% of them, 0.55, of the students, 55% will play a sport, and that leaves 45% who do not. And then of the people who play a sport, 6% of those play in college, which means that the other 94% of the players do not play in college. We currently don't have any information about the people who don't play a sport. We're kind of assuming that they probably don't want to go on to play, but we do know that walk-ons do happen. So what percent of high school students play a sport in high school and then go on to play on a college team? So the probability that they play in a college team, given that they played in high school, is going to be, we can just multiply down the line. So we have the probability that they play in high school times the probability that they play in college, given that they were in high school and played. So that's just going to be our 0.55 times the 0.06, which will come out to be 0.033. And they did ask what percent, so that is actually only 3.3% of all high school students end up playing in college. Another thing that we could ask here, what percent of high school students who do play a sport in high school do not end up playing in college? So that one would be the probability that they play in high school times the probability that they do not play in college, Again, 55% of them play in high school, but of those 55%, 94% do not play in college. So that means that 0.55 times 0.94, 51.7% of all students do not go on to play in a college team. Make that look more like a 5 and a 1. Example 2. The Pew Internet and American Life Project reported that 79% of teenagers aged 13 to 17 use social media, and 39% of teens who use social media feel pressure to post content that will get popular and get lots of comments or likes. So, 79% use social media. If 79% use social media, 100 minus 79 would be 21% do not. And again, because these are early examples, I am just focusing on one branch, but we could actually have other information about people who do not use social media, but might still feel the pressure to post, even if they're not allowed to use it. But of the people who do use social media, they can either feel pressure or no pressure. 39% of the people who use social media feel pressure, 0.39. And then the rest, 1 minus 0.39, the other 61% don't actually feel that pressure. So what percent of teens age 13 to 17 use social media and feel the pressure? So that would be the probability that they use social media times the probability that they feel the pressure given that they use social media. And again, all of these conditional probabilities are just from anything beyond the first branch. Again, just to find the overall percentage, you just multiply down the line or down the branches that you want. So our 0.79 times our 0.39, 0.79 times 0.39 is 0.3081. But they said what percent? So that is 30.81% of teens aged 13 to 17 both use social media and feel that pressure to post popular content. And what percent of teens do use social media but don't feel the pressure? So now we're going down the other branch, going the 79, then the 61. So that would be 0.79 times 0.61 is 0.4819, or 48.19% of all teenagers age 13 to 17 will use social media but not really feel any pressure to post. And again, if we look at the 48.19% plus our 30.81%, altogether that is the 79% who use social media. And if we add in the 21% that don't, that's all of the people involved. Example 3. Shannon hits the snooze button on their alarm 60% of school days. If they hit the snooze button, there's a 70% or 0.7 probability that they make it to their first period class on time. If they don't hit the snooze button, there's a 90% or a 0.9 probability that they make it to class on time. So Shannon has two options. They either snooze or they do not snooze. If they snooze, there's a 60% chance that that'll happen, so that's 0.6. And that leaves the other 40% chance that they do not hit the snooze button. If they do hit the snooze button, there's a 70% chance that they are on time, or 0.7 that they are on time, which leaves another 30%, 0.3, that they're late. On the other hand, if they don't sleep in, if they don't snooze, there is a higher chance, a 90% chance, 0.9, that they are on time, which leaves only a 10% chance, or 0.1, that they are late. So what's the probability that Shannon hits the snooze button and is late? So if they hit the snooze button and end up late, that would be the 0.6 from hitting the snooze button times the 0.3 from being late after hitting the snooze button. 0.6 times 0.3, I believe, is 0.18, but I'll double check my math. Yeah. 0.18. They just said probability, so that is a perfectly good answer. You could also say that's an 18% chance, or we could turn that into a fraction and reduce it. That's also a 9 out of 50 chance. So if they hit the snooze button 50 times, 9 of those times they're likely to be late. What's the overall probability that Shannon is late? So if there was a 0.18 chance that they were late, given that they did snooze, we also need to find the probability that they did not snooze but still ended up being late. So 0.4 times 0.1 would be a 0.04 chance. And if we add those two late probabilities together, there ends up as a 0.22 chance, or an 11 out of 50 chance, or a 22% chance that they are late at all. Suppose we know that Shannon is late, what's the probability that they hit the snooze button? So again, this one we're just looking at the conditional probability, the probability that they snoozed, given that we know that they are already late. Again, that's the probability that they snooze and are late, divided by the overall probability that they are just late. So if they are snoozing and late, that was a 0.18 chance. And if they're just late, that's a 0.22 chance. So 0.18 divided by 0.22 is, there is an 81.8% chance, 0.818, or 81.818%, that they probably snoozed, since we already know that they're late. And finally, recently, Harris Interactive reported that 20% of millennials, 25% of Gen Xers, and 21% of baby boomers, and 17% of mature generations, the oldest ones, the silent and the greatest, read more ebooks than print books. According to the Census Bureau, 34% of those 18 and over are millennials, 22% are Gen X, 30% are boomers, and 14% are older, mature. Suppose we select a U.S. adult at random and record which generation the person is in and whether they read more ebooks than print books. So let's see here. We can have multiple branches depending on what we've got. So we want the generation to come first. So let's start with the oldest generations, the mature generations. That is 14% of the overall population, or at least it was at the time that this question was written. Next oldest would be the baby boomers. That is 30% of the population, 0.3. The next oldest group would be Generation X, 22% of them, are the overall population. And then finally, the youngest of these groups is the millennials. And that would be 34% of the population there. Now, 20% of millennials use more ebooks than print books. So 0.2 would be ebooks, leaving the 0.8 in print. Generation X would be 25%. Maybe I should have left myself more space. That means the other 75% of Gen X read more print books. Of the baby boomers, 21%, 0.21, read more ebooks, and 1 minus 0.21 would be 79%, 0.79, read more in print. And the oldest, here, let's go up to here, 17%, read more ebooks, which I believe is 83%. Do not, yeah. And there we go. So find the overall probability that the person reads more ebooks than print books. So we have to find all of the ebook probabilities and then add them together to find the overall probability that any of these people reads more ebooks. Here, let's do here. So of the oldest people, 14% of the population and 17% of them read more ebooks, so that is 0.0238. Of the baby boom generation, 30% of them are the whole population and 21% of them read more ebooks, so that would be 0.063 of the overall population. Gen X, that's 22% of everybody, and 25% of them read more ebooks, so that is 0.055. And then finally, millennials, 34% of the overall population, and 20% of them read more ebooks, that is 0.068. So, overall probability that they read more ebooks, we just take our 0.0238, add it to our 0.063, add those to our 0.055, and add those to our 0.068. So altogether, 0.2098, or 20.98%, almost 21% of the population reads more digital books than in print. And we'll do one more calculation of conditional probability. Suppose a person reads more ebooks than print books, find the probability that they are a millennial. So that would be the probability that they are a millennial given that they read more ebooks, would be the probability that they are a millennial and read ebooks, just divided by the probability that they read ebooks. So the percentage or the probability that they are millennial and read ebooks is that 0.068. Again, just going down for 2 millennials and then those who read ebooks. And from the last problem, we found that the overall probability of reading ebooks at all was 0.2098. Just double checking my work there. So that's a 0.324 chance, or 32.412%. And that's tree diagrams.